Hello everyone and welcome to my channel. My name is RF and in today's course we're going to talk about one of the very important theorem in circuit analysis known as Tellegen's theorem, and it relates to the conservation of power in a circuit. So let's very quickly get started. What is Tellegen's theorem? Well, Tellegen's theorem is a fundamental principle in electrical circuit theory that applies to any network, regardless of its linearity, time invariance, or other properties. It provides a way to verify the conservation of power in electrical networks. So for any lumped electrical network, we know that the sum of instantaneous power across all branches has to be zero. Why? Again, because of the conservation of energy. In an isolated system, the energy cannot disappear or increase unless there is an exterior force. There is a force imposed on onto that system. So the Tellegen's theorem in circuit analysis can be stated as the summation of Vk Ik, K ranges from 1 to n. In this formula, K is the branch and n is the total number of branches in a given circuit, and K is just the kth branch in that circuit. In order to figure it out better, let's solve a problem together. In this problem, we're going to calculate power in all the elements of the circuit below. What are the elements? These resistors and this battery or power source. So I'm going to calculate power. From previous sessions, we know that power in circuit analysis is nothing but voltage times current. That's the general formula of power in circuit analysis. But in order to calculate power in each and every one of these elements, what I need is the current. If I consider the current coming out of this battery or the power source as I know that once the current reaches to this node, it has to split into I1 and I2. Again, the conservation of energy tells me that I1 plus I2 has to be I. And I1 flows here, I2 flows here, so let me just follow I2 and I1's path. So I1 is also here. And I want to just call this small current as I3, which again peels off into I4 and I5. As you can see, I1 flows into 6 ohm resistor, I2 flows into 12 ohm. On the other hand, I4 flows into 10 and I5 flows into 40 ohm resistor. And we know that I4 plus I5 has to be I3. I hope you agree with me so far. In order to solve this problem, I really need to figure out the value of I. Because if I have I, the rest of the process would be just automatically simplified. If I want to find I, this circuit is a little bit complicated to figure out I in just one quick look. You might be able in future to just look at the circuit and figure out the most simple way of the circuit, like have it in one branch. But I'm gonna just walk you into how to do this. You see this 10 ohm and 40 ohm. From previous sessions, we know the definition of parallel resistors. If the tails and heads of two resistors are connected to each other, we can call them parallel resistors. So 40 ohm is in parallel with 10 ohm resistor. What is the equivalent? For two resistors, you know that it's 40 times 10 over 40 plus 10. That would be 400 divided by 50, or 40 divided by 5, which gives me 8. If you want to make sure that you have correctly calculated the equivalent resistor, just remember that in a parallel set of resistors, the equivalent has to be less than each one of them. So 8 ohm is less than 40, and it is less than 10 for sure. So I know that this is most probably correct, unless I've made some miscalculations. So I'm going to just simplify my circuit a little bit more. Let's see what we got here. That one was 6 ohms, if I'm not wrong. Yeah, that's 12 ohms. And then I just simplified the two resistors at the right, and the equivalent was 8 ohms. And look at here, 6 ohm and 12 ohm. Do you agree that the heads and the tails of these two resistors are connected to the same point? In other words, we call them same potential. These two resistors are same potential. So 12 ohm and 6 ohm are also in parallel. I'm going to show you a quick way to figure out the parallel of these two. If one of the resistors is n times bigger than the other one, in this example 12 is 2 times 6. Do you agree? 2 times 6. The equivalent would be the bigger one, which is 12, divided by n plus 1. N is 2. 2 plus 1, which is 3. 12 divided by 3 is 4 ohm. So remember, when we want to calculate two parallel resistors, is one of them is n times bigger than the other one, the equivalent would be the bigger one divided by n plus 1. And n is the scale. So 12 is 2 times 6. So the equivalent would be 12 divided by 2 plus 1. So these two equivalent resistor is 4 ohms. Let's make it even simpler. I have 30 volt here, and look, it's only one loop. It's only one loop, 4 ohm and 8 ohm. And now I'm going to use a very good feedback from previous session. If you remember, let's just see if we can very quickly figure out the voltage over 4 ohm and the voltage over 8 ohm from voltage divider. I know that 8 is 2 times 4, and from Ohm's law I know that resistor has a direct relationship with voltage. If 8 is 2 times 4, the voltage across 8 ohms has to be 2 times the voltage across 4 ohms. And from the conservation of energy, I know that V of 8 ohm plus V of 4 ohm has to be 30 volt. Very quickly I figure out V of 8 ohm should be 20 volt. On the other hand, the voltage across 4 ohm has to be 10 volt. Now you guys can tell me. I was looking for current I that flows out of the battery or the power source. I equals, you can use three methods: V of 4 ohm over 4, or V of 8 ohm over 8, or 30 volt over the equivalent resistor of 4 and 8, which in this case are in series. Let me just use the general rule. 30 volt divided by 4 plus 8, which is 12. That gives me 2.5 amp. Alright, I know that the main current flowing out of my source is 2.5 amp. Now let's have another look at the circuit. I know that the main current here is 2.5 amp. And this current has to be divided into I1 and I2 so that I1 plus I2 is again is 2.5. And this current is the same as I3 because they're in the same loop. They're in the same branch. And I3 is I4 plus I5. And I know that I3 is the same as I1, which is 2.5 amp. Now let's break it into pieces to figure it out. Right, I've drawn the circuit just to save some time. We have 2.5, which has to peel off into I1 and I2. Now I want you to remember the current divider rule. Let's just assume the Ohm's law, R equals V over I. From here, we know that R has indirect relation with I. So the resistance and the current has indirect relationship. What does that infer? That infers that if 12 is 2 times 6, that means that the current which flows into 12 has to be half of the current that flows into 6. Why? Again, because current has indirect relationship with resistance. The current of 12 ohm, it has to be half of the current of 6 ohm. And what I know from conservation of energy is that the current of 12 ohm plus the current of 6 ohm has to be 2.5. And if you remember the current divider rule, I know that the current of 12 ohm is the other resistor, which is 6 ohm, divided by 12 plus 6 times the source current that flows into both of them, which is 2.5. 12 plus 6 is 18. 6 over 18 is 1 over 3. So the answer is 2.5 over 3 or 0.83. That's the current of 12 ohm. So very quickly, I come to the conclusion that the current of 6 ohm is 2.5 minus the current of 12 ohm, which is 0.833. That would give me 2.5 minus 0.833, 1.667. And this is the current that flows into 6 ohm resistor. Okay, I know the current, I know the resistor, but do I know the voltage? If you remember here, I just calculated the voltage. This 4 ohm here is the equivalent resistor of 12 and 6. And as 12 ohm and 6 ohm were in parallel, they have the same potential. And the potential is the same potential across the 4 ohm resistor, which I just figured it out. It was 10 volts. So I know the voltage across 12 ohm equals the voltage across 6 ohm, and it's 10 volts. Okay? And I know the current of 12 ohm resistor is 0.833 amp. Now it's time to calculate the power of 12 ohm. The power of 12 ohm is 0.833 times voltage, which is 10 volts. That gives me 8.33. And I hope you remember the unit of power, which is watt. And on the other hand, the current of 6 ohm resistor is 1.667 amp. From here, I come to conclusion that the power of 6 ohm resistor, the power that 6 ohm resistor consumes is 1.667, which is the current, times the same voltage, 10. That gives me 16.67 watts. Okay, we still need to figure out two more powers, the power across 10 ohm and the power of 40 ohm resistors. I know the current that flows into the combination of 10 and 40 ohm again is 2.5 amp. The current of 10 ohm plus the current of 40 ohm resistor has to be 2.5 amp from here. Okay? And let's just save some time very quickly. The current of 10 ohm is the other resistor, which is 40 ohm, divided by 10 plus 40 times the main current, 2.5. 40 divided by 50 is 4 over 5, or 0.8 times 2.5. That gives me 2 amp. So it's easy to figure out the current of 40 ohms. The current of 40 ohm is 2.5, the main current, minus 2 amp, which is the current flows into 10 ohms. That would give me 0.5 amp. That's the current of 40 ohms. Okay. And I know that the voltage of 10 ohms equals the voltage of 40 ohms because they're both in parallel, and that is 20 volts. Again, if you guys want to remember, I will refer you to the equivalent circuit, this circuit over here, that we simplified. This resistor of 8 ohm is equivalent of 10 and 40, and the voltage across it was 20 volts. And this 4 ohm was the equivalent of 12 and 6, and the voltage across it was 10 volts. So here, the last step is to calculate the power. The power of 10 ohm is the current, which was 2 amps, times the voltage, which is 20 volt. 2 times 20 is 40 watt. On the other hand, the power of 40 ohm equals the current, which is 0.5 amp, times voltage, which is the same, 20 volt. That would be 10 watt. So far, we calculated the power of all consumers, or all the resistors. But I also had a 30 volt power source. If you remember, I also have the power source. What about the power source power? Over here, the power source generates or delivers power into the circuit. So the power of the power source mathematically is calculated the same way. Is voltage, which is 30 volt, times current, the main current of the source, which was 2.5 amp. 30 times 2.5 equals 3 times 25, or 75 watt. This is the generated power or delivered power from the power source. So I have a total of 75 watt from the main source. And from Tellegan's theory, I know that the power delivered by the power source has to be equal the power consumed by all the consumers or the loads. So the power delivered is right here, 75 watt. The question is that, does 75 equals all the consumed powers? Let's just write them down one by one. I have 4 consumers, 12 ohm, 6 ohm, 10 ohm, and 40 ohm. And the consumed power is 8.33, that's the 12 ohm power, 16.67, 40, which is the 10 ohm power, and 10 watt over here. I'm gonna just write them all down. Well, as you can see, 40 plus 10 is 50, and 16.67 plus 8.33 is almost 25. So at the right side of the equation, I have 50 plus 25, and on the left side, I have 75. So have I met Tellegan's power theorem? The answer is yes. And in all circuits, this is always fixed, that all the delivered powers from the power sources has to be the same as all the consumed powers. Why? Because the power is conserved. Thank you very much, everyone, for listening and watching my video. Please, if you liked the contents and if you think it was helpful, do like it and share it, and do subscribe into my channel. Give me the motivation to provide more contents and solve more problems. Let's help each other grow. Thank you very much. Have a wonderful day, everyone.